Okay, so Sydney asked me to introduce myself while we're getting set up here. I'm Damian Rouson, president of Sorcery Institute. It's a nonprofit network of independent professionals who apply modern software development practices to computational science projects. We do some training classes, consulting, research, open source software development. And I'm going to co-present today with Alessandro Fanfarillo, who's a postdoc at the National Center for Atmospheric Research. And since Sydney said she raised an eyebrow, I thought maybe I should set the scene some by, I'm going to pick up on what an earlier speaker did and survey the audience a little bit. How many of you used a Fortran code today so far? Okay, so about maybe 1/4 of the audience.
20 years ago.
Now, how about if I, okay, you're the perfect plant right in the front row here. How about if I demonstrate to you that you probably used one today? Who checked the weather? People I talk to in weather science tell me they don't know of a single operational weather model that's not written in Fortran. So Fortran helped all of us get dressed today, figure out what to wear. How many of us are in one of the, I think, 196 nations that signed the Paris Agreement for the climate and didn't elect someone who's going to revoke the whole thing? Okay. You can perform observations on the current weather and observations to detect what the climate was like in the past, but obviously you can't perform experiments on the climate. So anytime we're doing predictions of the climate, we're using the results of Fortran codes. I talk to climate scientists who tell me they don't know of a single operational climate model that's not written primarily in Fortran. So it still has a great deal of impact, and I guess therefore it's not surprising that I'm working with someone at the National Center for Atmospheric Research. So. Oftentimes when I'm teaching tutorials, and this one is really, it's sort of a blend of a talk and a tutorial. Usually with tutorials, I write code live like a number of people have done today, but this time we're just going to sort of walk you through important features in the language and how they're addressing changes that are coming in high-performance computing. But I will at the end point you to a virtual machine that you could download from our website that enables you to try out all the features that we'll talk about, almost all the features. Usually, oftentimes in tutorials, I'll start out by asking people if anyone knows what the shortest standard conforming Fortran program is. Anybody have a guess at that? Those of you who've written some Fortran? The shortest standard conforming Fortran program.
In lines or characters?
Characters. I think somebody said it. What's that? Yeah, so it's just the keyword end, okay? Now, what's the shortest standard conforming parallel Fortran program? It's a trick question. It's essentially the same thing because Fortran is now a parallel programming language. As of Fortran 2008, you could take any Fortran program and compile it with certain flags that would start the program up in a single program, multiple data form of operation where multiple replicas of the program will launch, which Fortran refers to as images, but the language standard is careful not to ever define precisely what an image is. One compiler and runtime library might map images to processes, or for example, MPI ranks. Another compiler and runtime library might map images to threads. So all these different replicas of the program start up, let's say images 1 through n, and each then executes asynchronously up until the point when one of them encounters some form of barrier. For example, sync all is a statement that's in the language now. And at that point, everyone will wait until everyone gets to that point. Sync all synchronizes globally, so there could be lots of waiting involved, and that's something that we won't want as we get to the exascale, so we'll see how we address that. You can try to fine-tune things by only synchronizing across a set of images instead of all of them. That can help some. But oftentimes, at least in the kinds of things that I care about, my training is in fluid dynamics. Even if I only have to wait on my nearest neighbors are waiting on their neighbors, and so it ends up being pretty close to being a global barrier for everybody anyway. Fortran uses a one-sided communication approach, which I'll show on the next slide. It's a partitioned global address space language. And in order for that to work, if I'm going to go and access data on another image, I need to know that that data is there. So any allocation or deallocation of a co-array, the co-array is the parallel data structure that's built into the language now, is also an implicit synchronization point. So let's look at this partition global address space syntax. We can imagine that using the SPMD style, each image is running the same code. It, of course, may take different branches through that code based on conditional statements. And so let's say each image is executing the line that we see here. A co-array is a data structure that has one set of dimensions that are our regular dimensions in parentheses, which is what you're used to seeing with Fortran arrays traditionally, but also has a second set of dimensions that are in square brackets, and those tell us what image we're on. And you can also have multiple dimensions and multiple codimensions all the way out to some total of 15 dimensions plus codimensions. So in this case, we're working with an array coarray, which sounds redundant, but what that means is that if I were to drop the square brackets, I'd still be dealing with an array. You can also have scalar coarrays, which sounds like an oxymoron, but it would mean that I didn't have any parentheses there, and if I drop the square brackets, I'm just looking at a scalar. And the square brackets are just there for communication. So on one image, this statement is going to grab data from image 2 on the right-hand side. It'll take element 2 and copy it into element 1 on image 1. On image 2, executing the same statement, it'll be a local copy, and likewise for the other images. One of the things that's interesting about, that's nice about this syntax that gives you a way to a minimally invasive way to parallelize legacy codes is that you only need to show the square brackets where you want to do communication. If there's no communication happening, then you can drop them, and that could be, the square brackets can be implicit. So you notice I don't have any square brackets on the left-hand side. It's as if I had square brackets there, and inside them I called a Fortran intrinsic that's named this image. Okay, so that means that the nice thing is that with parallel programming, obviously you want to know when communication is happening, or at least when it can happen. So I know when I look at the program, I can see quickly where communication can happen because I see square brackets. But you also want to not have to change code where you don't need to do any communication. So I've actually parallelized legacy Fortran 77 codes where lots and lots of lines didn't have to change. I might even be passing a coarray into a subroutine that's pre-existing that was written in a serial fashion, but if I'm only passing the local portion of the data, that subroutine doesn't have to change at all. So the call doesn't change and the subroutine itself doesn't change. I haven't said here what A is. The coarray feature is integrated into the language such that in addition to being various intrinsic types like reals, integers, or complex numbers, a coarray can also be of a derived type, which is Fortran's term for class. So I can have an array coarray here that has one regular dimension, one codimension, and that can be an object with all kinds of data inside of it, and I can communicate objects in a distributed fashion. And I'm showing here an allocation, what that looks like, and the asterisk there essentially is the number of images. It's not something that I'm allowed to set in the source code because the language is encouraging you to write code that's general so that you wouldn't want to tie your allocation to a specific, to a requirement to have a specific number of images. So that gets set at program startup to the number of images. You can also have more complicated user-defined communication patterns. For example, if I show the square brackets on both sides of the assignment and execute this on image 3, then image 3 can direct data from image 2 to be moved to image 1. Okay? So that's the basic parallel programming model that came into Fortran in the Fortran 2008 standard, which was actually published in 2010. There is now coming a Fortran 2015 standard that exists already in draft form and will be published officially this year. And when people often would ask me why I'm writing Fortran, it's the world's oldest programming language, if I try to crystallize it in one statement, the thing that I most often say is that it's the only language that has an international standards body that sees scientific programmers, and by extension HPC developers, as their target audience. And there are all kinds of features that come into the language because of that. And specifically, a lot of features that address challenges that we expect to face at the exascale. So that's what we're going to focus on today. Those challenges include much higher levels of parallelism on a single chip. And we'll talk about the features that come out of that. We'll talk about events, collective procedures. Atomics is something that we won't cover directly, except that events are actually an encapsulated form of atomics. Heterogeneous hardware within a single chip, where you might have fat cores and thin cores, or you might have graphics processing architecture moving onto the processor, and higher failure rates. This is an example where I'm saying They see scientific programmers, and specifically HPC programmers, as their target audience. And Fortran, as far as I know, is the only mainstream language that is already beginning to address fault tolerance. And so the portion of the talk that Alessandro will present to you is work that he's been doing as part of his postdoc on a language facility that exists in the draft standard of Fortran 2015, and that, thanks to him, the GNU Fortran compiler will be the first one to actually support, which is the ability to detect if an image has failed. And lastly, we have a capability for controlling groupings of arrays at once, which we're referring to here as locality control. But basically, it's teams. If you were an MPI programmer, you could think of it as communicators, basically. And oftentimes, under the hood here is MPI or OpenMP or pthread, something like that. So let's look at the Fortran 2015 features that target the exascale. The first one I'll mention is events. And an event is an intrinsic derived type. So in other words, it's a class that's provided by the language itself. And it encapsulates a private integer. So it's an atomic integer that you can use as a counter, basically. And you can use it to do segment ordering, to say, to roll your own form of ordering where I want this segment of code to execute before that segment, this segment of code on this image to execute before that segment on that image. And I can organize that with events without having to have all the waiting that we saw with the synchronization. And so I can declare an event co-array here, greeting ready. Let's say I'm going to have a hello world program where image one is going to grab greetings from all the other images and print them out. And we're going to loop through that where after it's grabbed the greeting, it's going to signal to them that it has the greeting. So I'll have a greeting ready for each image to signal image one that its greeting is ready for pickup. And OK to overwrite for image one to signal that it's OK to go on to the next step and write your next greeting. And I can use events through 3 statements or procedure calls that are now in the language, which is an event post, which atomically increments the account by 1, event query, which checks the count, and event wait, which decrements the count. Again, thinking about the importance of performance to scientific programmers, and especially parallel performance and things like vectorization, there's also a feature that came in with Fortran 2008 that we're not going to talk about in detail, but it's loop concurrency. It's do concurrent. Fortran gives the programmer, in many cases, the ability to communicate certain properties of the code and then leave to the compiler how to exploit those properties with certain optimizations. And do concurrent is telling the compiler there's no data dependencies between passes through this loop. So most compilers these days are vectorizing do concurrent. Some might multi-thread it. But the language is careful about the semantics to prevent you from shooting yourself in the foot, to do things like an event post, which will oftentimes be a remote operation, or event wait, which involves a lot of waiting. You wouldn't want to do that kind of thing inside of a do concurrent loop, and the language prevents that by saying that you can't do any image control inside a do concurrent. You can query inside do concurrent, and queries have to be local, so that's at least some help there in terms of performance. So let's say we have this greeting ready co-array, and image 1 just needs to check with the images 2 through n, so we'll assume that the first element there at the top is corresponding to image 2. So we're operating asynchronously here, so everybody's moving along at their own pace, and they might be at some point in time at different points in the code. And then image 1 gets to the point where it's already maybe created its greeting and printed it, and it's ready to grab the greeting from image 2, so it's going to query that event, in other words, that element of the event type co-array, to see if the greeting's ready. And maybe it turns out that the greeting's not ready, and so it'll move on, right? So not the kind of waiting that we saw with the bulk synchronous approach that we were using with Fortran 2008. So at some point, maybe image 3 will post to image 1 that its greeting is ready, image 1, but it won't wait. It will move on. At some point, maybe image 3 is ready to create, it's moved through to the next pass of the loop, and it's ready to create its next greeting, and it wants to overwrite the greeting, but it's going to, at this point, execute an event wait, because it wants to know if it's okay to do that overwrite. Image 1 now gets to the point where it queries the event for image 3 and says, and it sees that that event has been posted. In other words, the count has been incremented. And so now image 1 will post to image 3 and say, okay, you can overwrite that data now. I've gotten it already. So there are a number of constraints that I guess actually I've touched on some of these already that are performance-oriented constraints, like you can't put a post or a wait inside do concurrent, and also that query and wait have to be local. And you do the kinds of things of this that you might with atomics if you're writing MPI, where you're going to do things like create spin query work loops and a lot of the same algorithms that you might write with any parallel programming model, but now you're going to get to write them in the standard form of your language without linking to any external libraries in the source code, without having any direct calls to MPI, and leaving it to the compiler or runtime library team how to resolve those, the syntax that you're using into those calls. So the goal then with a lot of current work in terms of getting towards higher levels of parallelism, as I mentioned, is to not wait and instead to try and overlap computation with communication. So this is just showing you kind of what that looks like if we had two images running, if we had a sync image execute, and we've done what we can. Let's say we're working Fortran 2008 and we don't have the Fortran 2015 events yet. We at least don't want to go with sync all and have a global barrier, so maybe we at least only synchronize with our nearest neighbor and say that's image 2, but we have to wait there until image 2 gets to execute its corresponding sync images statement to synchronize with image 1. So there's idle time there. The idea of events, as you've seen from the example we went through so far, is that image 2 can instead just post an event and move on. And image 1 doesn't have to wait until it's absolutely necessary. Teams, as I mentioned, are groupings of images. And the idea is that with teams, you can synchronize just within the team. So this is largely inspired by multi-physics models like climate models, for example, where you've got an atmospheric model, an ocean model, you've got a land ice model, a sea ice model, and they each are operating on different timescales, and you don't necessarily want to couple them all globally and force a synchronization in one part of the model to cause a synchronization in other parts of the model that don't necessarily need to synchronize yet. And so teams will give us the ability to collect images into groups. And this is actually one of only, I'd say, I think this is the only feature that I'll talk about today that's not yet in the G-Fortran compiler. But I mention it partly because it plays a role in the way the standard defines the collective procedures, which are really important. We'll see in a moment some of the performance implications of having a good set of collectives. And the idea of collectives is that each non-failed image in the current team must invoke the collective. Okay, so we're starting to see some fault tolerance come in there, and this is language that's fairly close to what's in the standard. And a parallel calculation / communication happens, and the result can be placed on one image or all images, depending on what arguments you passed. Some of the arguments are optional, like the stat is how we're going to figure out if a failure has happened. Alessandro will show you that a bit later. Result image is if I'm doing a reduction, I want to be able to say where the result goes. Source image is if I'm doing a broadcast, I want to be able to say which image is providing the data. And all the collectives have a first argument named A. I don't know why they chose that name. And its intent is in-out, meaning I can both pass data in, get data out from it. And no implicit synchronization happens at the beginning or end of any of these collective subroutines that are in the language now, and that's really important for performance reasons. However, since there's no implicit synchronization happening, we do want to at least make sure that the data that we need is available, and so there's also a statement in the standard that no image's data can be accessed before that image invokes the collective subroutine. So there's a pretty small set of collectives in the language now, and at least one of them is extensible. We have co-broadcast for distributing data, co-max, co-min for extrema across global distributed data sets. Was there a question in the back?
So is this all for co-array Fortran? Or is
That's a really good question. I had actually been working with co-array Fortran for 2 years before I actually realized that it's not, you don't necessarily have to use these just with co-arrays. In fact, so when I first read that, I thought it was co-array broadcast. What it actually is collective broadcast. And there's a lot of interesting, so any embarrassingly parallel problems, there are a lot of important scientific problems that are embarrassingly parallel, you could actually do most of your computation just with what we've seen so far, just synchronization and collectives, to do things like compute statistics across some global data set. And that argument A doesn't have to be a co-array. You can pass in any variable you want.
It's across nodes, and does it
Yeah, so
somehow with MPIs in the future?
yeah, so actually what ends up happening in the default case, I lead the development of a library called Open Co-Arrays, which was started by Alessandro, who wrote the core runtime library. Essentially, one chapter of his dissertation is now this open source library that's been downloaded a couple thousand times worldwide, which I think is a pretty good bang for the buck out of one chapter. And what Alessandro did is he gave us an option to use several different communication libraries. You could use MPI. He also developed a GasNet version of it, did some investigation into ARMC, but we decided not to go down that path. But let's say in the MPI case, which is the default case, then things like MPI, I think all of these actually end up being wrappers around MPI reduce. Is that right?
Yeah.
So, and I don't know what the corresponding ones would be if you use other libraries, but yeah, you could think of these as MPI reduce. Okay, so just to give you one example, cosum, to talk about the way this operates, in square brackets are the optional arguments. So if I don't give a result image, then I'm saying I want everybody to get the result. So the A will get overwritten. And in this case, since we're talking about a mathematical operation like sum, it needs to be a numeric type. So we don't have an ability to apply this to objects yet, at least for cosum. Some of the other collectives like co-broadcast you can apply to objects, what Fortran calls derived types. And we've talked about a good amount of this already, so I think I'll just move on from there. But let's talk about how it actually operates. So let's say we have a co-array that's distributed across our entire computation. We've grouped some of the images into teams, strictly for purposes of reducing the amount of global synchronization. And we're now going to call a cosum, and since all the additional arguments beyond the first one are optional, we'll just pass that first argument, and everybody will get the global sum. Oftentimes when I've used it, A has just been locally a scalar, so it's a scalar co-array. So there's no parentheses, but there's square brackets when I declare it. And, but in this case, we're going to say that A is an array, and we're going to look at the first four elements of that array. So a lot of the same Fortran 90 notation that you could use with regular arrays, you can also use with co-arrays. So 1:4 means I want to talk about the first four elements of that array, and the 1 in square brackets means I'm talking about it on image 1. So we call the cosum, and then what we end up with is a sum over basically a column-wise sum, so that on the first element on image 1, we end up with 0 plus 2 plus 3, so we get 5. And then the second element, we get 5 plus 6 plus 4, so we get 15. But that happens only within this team, team 1. And team 2 gets a different set of results based on what portion of the co-array it has. So in Fortran 2008, if you wanted to do that same sort of operation, you would write your own collective using the square bracket notation and grabbing data from where you need it. And so I wanted to look at a comparison between what it would be like if you did that for yourself versus calling the collective. And the difference is quite substantial. I mean, basically what this is saying is it's important to have collectives in a parallel language. You can see a difference of anywhere from a factor of like 2 to almost 10 between the bottom two curves are just calling the collective to do the sum. The upper ones, in some cases, are some reasonably sophisticated approaches, either a binary tree or there's something called an alpha tree. So we have binary tree, recursive doubling, something called an alpha tree, which is a one-parameter family of algorithms. Depending on how you set that parameter, it can be a binomial tree or recursive doubling. And we chose alpha can vary from 0 to 1, and there's a paper in the literature that kind of recommends a value of about 0.4, so we picked that. But nothing came anywhere close to just calling the MPI, the collectives which are wrapping MPI. And the basic reason is because when you're doing these collective operations, there's so many variables you have to take into account related to message size, network topology, and network, I guess I said that. So the important thing is you want to be able to have collectives that you can call. This is a similar plot for code broadcast. We've got a binary tree algorithm here and a binomial tree algorithm, and we're comparing them to the language intrinsic collective. And again, you can see there's a significant difference in performance. So right now, the G Fortran supports this because of the Open CoreArrays library that Alessandro developed. And the Cray compiler provides these. The Intel compiler supports pretty much all of the Fortran 2008 CoreArray features, but doesn't support the 2015 features yet, like these collectives. So I think that kind of shows, though, the importance of pushing on the vendors to support the latest standards. And this is Alessandro's part of the talk.
Yeah, thanks. What's the laser?
You know, I haven't tried it. There we go.
Okay.
Yeah.
So yeah, you are HPC people, so you know why we need fault tolerance. But anyway, just to be sure, let me say that the next Exascale machine will be equipped with millions of nodes, and every node will be equipped with thousands of cores. And if a single node fails about every year, we are going to have a failure on an Exascale machine every 30 seconds. These are statistics taken from a paper from Jack Dongara's group, I guess. And if we have a node that fails every 10 years, on average, we are going to have 5 minutes of mean time between failures, so it's nothing, basically. And even if, in a very theoretical case where a node fails every 120 years, something impossible, I guess, we are going to have one failure every hour, mostly. So the checkpointing restart approach that has been useful so far on petascale machine will be not effective with this sort of failure rates. So we need to care about, we need fault-tolerant applications mostly. So failed images is the feature introduced by Fortran 2015 that allows you to detect failures, but doesn't provide any support for the recovery strategy. So basically, Fortran tells you, here there are 3 functions, actually it's 1 statement, 2 functions, and a constraint that will allow you to detect failures. Then how you recover it, it's up to you. So basically, the first statement is about simulate failures. So if you want to test your algorithm, you want to test a failure. So when your image executes fail image, the image will die, basically. So you can test your algorithm with random failures or specified failures introduced in your code. Image status is a function that checks the status of a specific image. Basically, it takes as argument an image index and returns the status of that image. So in Fortran 2015, an image can be in 3 possible status: running, stopped, or failed. Failed is where an image is not reachable anymore. Stopped is where an image has gracefully stopped the execution. The main difference between these 2 status is that a failed image it's unreachable. The data has gone. Whereas for a stopped image, the image is not running anymore, but the data is still available. So you can do something about it. And finally, in my opinion, the most important function here is failed images, which returns you the list of failed images from the point of view of the image that execute that function. And the last statement is a little bit tricky, but it's essential. So because now CoreArray assumed that an image can fail, so it's not there, it's pretty similar to an I/O operation. Basically, in Fortran, when you have an I/O operation, you may have a problem when you access your file. You may not have enough rights to access that file. The file may not be there, or with the wrong name, or whatever. So in case of I/O operation like this, if you don't pass any stat equal attribute, your program will crash because the program doesn't have a way to tell you that something went wrong, something unexpected went wrong. The same thing happens with CoreArrays now. So if you try to get data from a dead image, you should pass this attribute because then you can check that actually the transfer was completed correctly. If you try to get data from a dead image and you don't pass that stat equal attribute, the Fortran standard forces you to crash because you don't have a way to check that everything went well. And this is an example. So let's imagine we have this configuration here and a failure strikes on image 4. Because we are calling a sync call, and if you are familiar with MPI, sync call is practically equivalent to an MPI barrier, all the images will detect the failure, basically, because all the images have been involved in this barrier. And this status here, this status variable, will have this value, basically, this stat failed image, which is a constant value introduced by the standard that tells you, look, before this sync call, something went wrong. And because you are checking this condition, you can do something about it. If you have a failure here before this sync call and you don't pass this stat equal attribute, the program will crash because the standard enforces you this. The standard wants you to check this condition. So just to give you an idea of the advantages of these new Fortran 2015 features, I'm going to show you a performance result coming from the parallel research kernels. Basically, parallel research kernels is a suite of several scientific kernels. You can Google on the internet. There is a GitHub available with a bunch of implementation of these kernels in several languages, including Core Fortran 2008. And what we have done is that we have taken these basically two kernels, the peer-to-peer synchronization and 2D stencil from Fortran 2008, and we transformed those two codes into Fortran 2015 using events. And the first kernel is the sync point-to-point kernel. Basically, it's a stencil with a demanding data dependence resolved using a software pipeline techniques. So basically, imagine that you want to compute something on this point, and the pattern here is that you need the data from the left neighbor, the top neighbor, and the top left neighbor. So because of this specific dependence, you can proceed in a pipelined way on your metrics. So you can compute all the first column, then you can compute the first element on the second column, the second element, and once you have computed that, you can start computing, the third element of the second column and the second element of the third column. In a parallel environment, you will have something like this. So you partition by rows, you give the first and something rows to the first image, the others to the second, and then you have this sort of dependence. And you can resolve this dependence using events because they are really fine-grained. This situation with sync images, it's really difficult to manage because sync images enforces you to wait for the other process. It's like a point-to-point synchronization that basically locks both images that are running. In this case, you can just, for example, image 1 posts an event on this particular column of image 2, and image 2 can wait just on this column and can keep going while this other image is computing the other columns. So it's a really fine-grained synchronization mechanism that brings this nice performance improvement here. Basically, this is a weak scaling case on Stampede. And of course, you see this different because we are passing from the shared memory to the distributed memory because Stampede has 16 cores on a node. But you can see that the difference is pretty big. This is the 2008 approach with sync and sync images, and this is the approach with events, just because of the finer synchronization mechanism, nothing else. And then with the Stencil kernel, we have one of the most common communication patterns, which is the hello exchange. Here, events can be used, for example, on each side to speed up a little bit the things. So imagine you have a 2D grid like this, and every square is owned by an image. Because Fortran stores the data by column, you can start computing applying your stencil by column. And once you have finished the first column, you can post an event on your left neighbor saying, look, the data that you want are available. If you want, you can get it. Without waiting, it's just a post that is asynchronous, it's not blocking. And you can keep going computing. Then when you finished your first row, you can say to your top neighbor, look, the data that you want is ready, and so on. So you have a little bit more overlapping by using events compared to sync all. And as you can see, the improvement is not huge, of course, but it's something. And this comes directly from the finer grain synchronization. So, okay, this is yours. Basically, the message is you can deal with situations that were really difficult to manage before these new features with Fortran 2008 features.
Okay, good. So even though we didn't actually write any code live here, as I typically would do in a tutorial, I wanted to at least mention that you can access most of the features that we're talking about. So let's see, GCC 7, which is going to be released imminently, I would imagine within the next week or two. And you can also already access by downloading the source and building it, which is what we've done inside the virtual machine. GCC 7 supports pretty much all the Fortran 2008 parallel features we talked about. You know, co-array, declarations, allocations, sync all, sync images. And from Fortran 2015, it supports events, collectives, and atomics, which we haven't talked about in detail. Teams are not yet supported, but failure detection, Alessandro has already developed a patch for G-Fortran, and it has been submitted for review, and once that's accepted, then that will be in whatever is the next release. So what's going to come out shortly is 7.1.0. If we're lucky, maybe his patch will be in 7.2.0. And you can download that from the Sorcery Institute website. It's sorceryinstitute.org/store, but it's a free open source virtual machine. It's also used in a graduate course that I teach here at Stanford. And there are a number of video tutorials online. Those were done about 2 years back, and so they were using the Intel compiler because Alessandro hadn't published his dissertation yet, so G-Fortran hadn't supported co-array Fortran yet. I'm oftentimes asked who's using this stuff. So I don't know if the slides are being made available to everyone, but I've got a few papers that I like here, people using co-array Fortran, getting 33% speed up on 80,000 cores relative to an MPI code. I like to make the point that since we're wrapping MPI, obviously you're not going to expect co-array Fortran to be faster than MPI. However, if you compare the MPI that almost all scientific programmers are writing today, which is almost always two-sided MPI communication, if you compare that to the one-sided MPI communication, which is much harder to write, but which the runtime library can generate for you if you write co-array Fortran, you can actually get speed up by switching from co-array Fortran to MPI, even though the co-array Fortran is wrapping MPI. A plasma fusion code, a weather model, a bunch of different applications like that. So I think we're out of time. Did you want me to take any questions or move on to the next speaker? Okay, John?
So the OpenMP standard is getting very close to a Turing-complete language embedded in comments. Are all these new features, are they a superset of the features that are now planned for OpenMP 4.5, or what features, if not, what features are
Right.
not yet covered, and also what is the semantics of mixed mode with OpenMP and
Okay.
semantics?
Okay, so the way the co-array features came into the language, they should mix quite well. You can certainly mix it with MPI because it'll just be like having another MPI communicator. And you can mix it with OpenMP. So you could write a co-array Fortran code. I don't think Alessandro would necessarily recommend this, but you could write a co-array Fortran code that uses the co-array Fortran just for communication across node and then maybe uses OpenMP within the node. So that's one response to the question. The challenge that I see with OpenMP is that the standard, the most recent one I've seen was 4.5. I think there might be a draft 5 out, but there's still a lot in there that explicitly states it doesn't support modern Fortran, and even some not so modern Fortran features, like for example, pure procedures, which are actually Fortran 95. So in one sense, this is pretty far ahead of OpenMP because it integrates with the whole language. One area where Fortran 2015 is behind OpenMP is, I don't know if you were here when I mentioned do concurrent, so we have this loop concurrency, and that still needs a lot of work. So in 2008, we got the ability to write a concurrent loop. In 2015, we can control whether variables inside the loop are shared or not. And what we still don't have is reductions I'd like to see. So we're behind OpenMP in that regard. And also, the Fortran committee has intentionally chosen not to target offloading to accelerators. And I think the reason is because we've seen in the past where, those of us who are old enough to remember the 90s, we had floating point units which were eventually brought onto the processor. And, my understanding is that things are headed that direction with GPUs too. And so that's one place where Fortran 2015 is behind OpenMP, because you won't really see anything there that targets GPUs or other accelerators. But you can run all this stuff on Knight's Landing, because you can run any x86 binary on Knight's Landing, right? Any other questions? Okay.
We're going to hit for a break, but I'm going to take some time back from your leisurely lunch. If you'll return in 3 hours, greatly appreciate it.
Thanks.
Thank you.